Okay, so welcome to the Software and Computing Roundtable on July 6th. In the Software and Computing Roundtable, we are currently discussing data analysis in high energy and nuclear physics. Last month, we had a survey of modern analysis tools. And this month, we will discuss reproducibility, sorry for my bad pronunciation here, of experimental measurements. And we're using experimental results long after the data are published. This Software and Computing Roundtable will be unique in the sense that we will not have three shorter presentations around one topic, but rather we have a longer seminar today by Nicholas Wardle from Imperial College in London. And then afterwards, we have a discussion. So Nick's physics interests are beyond the standard model physics, in particular through precision Higgs measurements. He joined the CMS collaboration in 2010. During his time in CMS, he has studied properties of the Higgs bosons and searches for exotic Higgs boson decay modes, including decays to dark matter particles. Recently, he is developing statistical methods, including machine learning approaches to reinterpret Higgs measurements and searches and preserves the results for the future. He will cover that work in his seminar on can we really reinterpret data from the LHC.
It's very nice to be invited to this roundtable, and thanks to the organizers really for giving me an opportunity to talk to you all. So I should say that just a sort of a caveat that I wouldn't really consider myself a computing or software expert. When the organizers asked me to talk, I think what I realized was that there's some of the issues that I'm going to talk about in my seminar are really important, and I think will influence the design of our computing infrastructures for future experiments and how we move forward in high energy physics. So the slides I have here are based on a seminar I gave a while ago at CERN, and I think I went a little bit over time at that point. So hopefully I'll try and go a bit quicker through some of the things to make sure we stay on time. So the title of my talk is, can we really reinterpret data from the LHC? And of course my, here we go. Okay, sorry about that. Okay, so of course the short answer is yes, otherwise I wouldn't really be giving a very interesting seminar. And I wanted to point out first of all that we have a forum which is actually dedicated to doing exactly these kind of things at the LHC. So the forum is this one here. You can find it from the link that I put at the bottom next to the starting point. And you can join the mailing list for announcements about upcoming workshops. We tend to have regular workshops around one a year. Sometimes with dedicated sessions on long-lived particles or EFT interpretations or whatever. So recently we've also started having tutorial sessions specifically around reinterpretation tools, and all of those are recorded. So if you want to have a go or you want to see what the kind of software we're using, do have a look at those as well. Okay, most recently we also put out a recommendation for reinterpretations after run 2. So you know that the LHC has finished run 2 back at the end of 2018. And basically having looked at all the kind of information that is being published now with that data, we put together some recommendations on what really the emphasis of reinterpretation data or auxiliary data for reinterpretation should be. So this was published back in February, I think it was, and you can have a look in the link at the bottom there for the side post article. Okay, so sort of generally about reinterpretation, of course, you can't really reinterpret something without having some interpretation at the start of things. And it's really impossible to summarize all of the different types of interpretations that we can do and we do at the LHC, and in particular the ways that they're presented. So there's really all sorts of different presentations of our data that we have. So at the top left there, you see things like measurements of the couplings of the Higgs boson, and also searches for supersymmetry particles. So I don't know if, oh, sorry, I seem to have zoomed out, okay. And then there's things like precision measurements of cross-sections for various standard model processes and things like that. So there's really a whole array of things that we can do. And then where to find them. So typically whenever we publish a set of data and publish our interpretations, we include an entry in HepData. So HepData is this very nice tool that we can use to catalog the data that's contained in the paper, but also additional information, you know, like efficiencies and other things that are maybe not so super interesting to publish, but are nevertheless useful for reinterpretations. And the nice thing about this is that these come with DOI, so you can, of course, cite those particular results for reinterpretation studies. Okay, so on this slide, I just want to sort of try and summarize the sort of spectrum of where we are when it comes to presentation of experimental results. And I sort of like to put things on the scale of how easy it is to actually reuse the results that we provide. So usually there's a trade-off between actually being able to use a result, you know, from just lifting it from the paper and doing something with it to actually then how flexible that result is. So on the far left, you have things like exclusions and limit contours in some UV complete models. So, you know, you always see these MSSM style or SUSY style parameter scans where we exclude some regions of phase space. That's great because it's very easy for a theorist to use. You know, if you come and you want to know whether a particular point in your parameter space is excluded, you can just go look at this plot and then see whether or not the data have excluded that already. So it's super easy to use, but of course there's the most assumptions you can possibly imagine built into these limit plots, right? So there's really a lot of assumptions about the data, types of signals that we would see, and various other things. And then on the complete other end of the spectrum, of course, we have things like the efforts in terms of open data. So really releasing the data at the level of, say, reconstructed particles within our detector, which is great, right? Because you hardly have any assumptions in there at all, you know, other than how stable standard model particles should behave. But there's really a lot more in terms of the expertise needed to actually access that data. So there's a higher threshold for participation in actually using that data. And of course, all the stuff in between is you know, some balance between the two. So there's obviously a lot of benefits moving from one side of the spectrum to the other. And I think in general, what we should aim to do is try and add to these methods rather than necessarily subtract. But what I'm going to try and do is maybe highlight a few of them in this seminar and to give you an idea about you know, the kind of things that we do. Okay, so an example of measurements for reinterpretation. So one of the things I'm quite interested in is studying precision measurements of Higgs boson processes and then trying to use those to ascertain some information on some beyond the standard model theory. And so in Higgs measurements, what we typically have are these so-called Meaurements. So some ratio of a cross-section to a predicted cross-section for some process. So for example, it could be the gluon fusion process that gained with the Higgs that gained 2 photons. And usually this is fairly easy to reinterpret, assuming that only the total rate of some process is affected by your new physics. So for example, here, you can see a nice interpretation by this group Lilith, where they've taken this data that I have on the left. So they've taken the best fit points and the uncertainty bars, and then including some correlation information, they can re-parameterize those in terms of couplings of the Higgs boson. So here they have a model where they're just varying the couplings of vector-like or vector bosons to the Higgs versus fermion couplings to the Higgs. And you can see in the contours there that they do a relatively good job of getting somewhere close to what the fit is. But you'll notice that the sort of central values and the contours don't really overlap with what the experiments would actually report. And in this case, you can do a very simple thing to do one step better by just adding additional information on top. So the fact that we actually publish these uncertainty bars, asymmetric uncertainty bars, means that you can do this variable Gaussian approximation. So you swap out the correlation matrix with this thing in the middle, and then do the same thing, re-parameterize in terms of these couplings, and now you can see that these contours lie on top of each other quite well. So this is already sort of an indication that that this idea of reporting measurements, which we already knew was not enough, so we always add the correlations, but it's kind of telling us that the more and more precise we get, or the more and more precise we want to be, the more information we need to convey to the theorist. So in this case, of course, we need to include somehow non-Gaussian effects in the results so that they can be properly reinterpreted. Okay, another very popular method for reporting data is unfolding. So I won't go into too much detail about what unfolding is, but just to say that this diagram kind of gives you an idea about what unfolding does. So of course, we start off with some particle collision, which is happening in the vacuum where the protons interact, and then through a bunch of various processes, there's some smearing and reconstruction effects. After having gone through our detector, we can build something like an observed spectrum in the data. So the bottom right plot there is an example of just the pseudo rapidity gap between jets in a particular analysis from Atlas. And then we try and undo the effects of the detector in order to report data that somehow have the detector effects removed. Right? So the idea being that this data on the bottom left is no longer, you no longer have to know anything about the Atlas detector in order to use it, because all the detector effects from Atlas or CMS are taken away. And this is an example from a group which is using this nice tool Contour to make some constraints on a particular model. So this is a B-L gauge model where the authors took some data from the Atlas experiment and threw in a BSM model with this B-L gauge. And then they can make exclusion contours in the parameter space of that model. So this is all using just unfolded data. So the idea is that they don't need to know anything about the Atlas data, about the Atlas detector to make these interpretations. So that's great with unfolded data, but there are a few caveats and issues that usually go with that. So one is usually this requires some Gaussian approximation when you report these error bars that you use, and the uncertainties on the prediction. So this, these red shaded bands, there's usually some Gaussian approximation in there. And as we just saw, Gaussian approximations can lead to fairly large biases. There's issues related to regularization, which again, I won't go into too much detail here, but essentially this can also lead to very large biases when the response or how the detector reconstructs things is not super diagonal. And then there's some really tricky things like often these days, to get the best sensitivity out of our searches, we're using machine learning methods to extract the signal, right? So the example here is from a recent evidence paper for Higgs mu from CMS. And here they're using a deep neural network in order to extract the signal, which is this blue histogram in the stack there. And the point is, how do you unfold this to particle level? So there's information there that's sort of baked in from the detector that it's really tricky to actually unfold and then describe what those things are at detector level. So it doesn't really make sense anymore to talk about an unfolded measurement of something like a distribution of a neural net. So this is a sort of a problem for working in that unfolded space. So one idea which came out or has been quite popular in recent years is rather than sort of unfolding and trying to remove all these effects of the data to make life easier for the theorists is why can't we just do the interpretations in the folded space? So essentially this is what we're doing whenever we do an interpretation at CMS or Atlas or LHCb. So why can't we just give that same information to the theorists so that they can be reinterpreted using the same thing? And this isn't really a new idea. I mean, it's only recently that in the last few years that this has become popular, but certainly the idea has been around since the start of the millennia. And I just took a quick quote from this workshop on confidence limits, where it seemed to be fairly unanimous that the idea of publishing likelihoods in the reconstructed space is actually quite a good idea. Okay, so as I said before, I wanted to focus on just a few topics from this spectrum, and these are the two that I'm going to pull out today. So this concept of simplified likelihoods or full likelihoods, so really publishing the full likelihood information for reinterpretations. Okay, so what I'm going to do is try and lay out the sort of very basics of what an LHC style likelihood might look like, especially if you're looking for new physics. It's a fairly general form. It doesn't mean that every single search looks like this, but it's a fairly generic sort of approach that many analyses will take. And it turns out to be a particularly useful one in terms of writing down, specifying a full likelihood in a rather convenient way. So usually the likelihood takes this form. So you have these two terms here. So alpha would be our parameters of interest. So that might be the Higgs mass or some cross section for TT bar or whatever, and delta are the nuisance parameters, so things related to our experimental uncertainties that we have to include. And then this pi term is usually we think of them as priors or constraints on those nuisance parameters. So in the end, what you end up with is something like a simple product of Poisson probabilities. At the end of the day, usually what we're doing at the LHC is just counting events in a particular bin, and so we can describe these processes as Poisson processes. And so you end up with this simple product. Okay, so as I said at the LHC, we tend to use this this convention that we have these split into parameters of interest and nuisance parameters, and often when you're searching for something or setting a limit on something, there's usually a single parameter of interest, which is just an overall cross section scaling. So this parameter mu, which you see here. And then for this term Ni here, you can usually think of this as broken down into contributions from some signal process that I'm looking for and some background processes that I'm trying to deal with. So it's just a simple substitution. Probably you're familiar with this. And then, as I already said, these are often Poisson probabilities, so you can just replace these probabilities with Poisson terms. Okay, and I already mentioned the thing about the priors. Okay, so this is a toy sort of example that I cooked up to sort of illustrate this idea of building a likelihood at the LHC and what we can do to communicate the information better to theorists. So imagine this sort of fairly simple model, and this is somewhat inspired by, say, a search for supersymmetry or some exotic signature. And the idea here is you have just some single source of background, so that's this blue histogram here. Or you can think of this as the sum over multiple different backgrounds, but in the end it doesn't matter. You might say use Monte Carlo simulation or something like that to estimate what the contribution in each of the bins are. And then you have the observations in data. So the crosses there are just the number of events I observe in a particular bin. So here I'm not talking about a particular observable. I'm just labeling the bins 1 through 90. And then I've sort of split up the data here into sort of 3 categories. So this is often done to improve the sensitivity because the signal to background ratio might be different across different categories. And so in this case, we just have 3, where within each category you have 30 bins, and the signal to background is increasing with bin number. Okay. So then there are the uncertainties that we have to consider as well, right? So usually whenever you predict the contribution from a background or a signal, you have to consider the uncertainties on that prediction, and the typical ones that we have to deal with are things like efficiencies and luminosity uncertainties and those kind of things. And so here I'm just including 2 sort of overall uncertainties on the background. So I'm just labeling them efficiency and scale factor. It doesn't really matter what they correspond to, just to say that they are uncertainties on the total number of background events in each category. And then there's, for each of these bins, there's an uncertainty which is uncorrelated between the different bins. So as I said before, a typical route to estimating what this blue histogram is to generate Monte Carlo simulation, and you may have some limited resources to do that, and so you'll end up with some uncertainty on that. And so that's what these blue shaded bands just represent, just the uncorrelated uncertainty in each bin. Okay, so then finally, I've also included two additional uncertainties which are correlated between the bins. And I'm just giving them the labels energy, scale, and theory, but again, it doesn't matter what they are. Effectively, the idea is that they just change the slope of the background, again, within each category. So in the end, this gives me a total of something like 94 nuisance parameters that I have to deal with. Okay, so in this case, you can think of just the expected number of background events in a given bin as, if you like, the fraction of events in that bin multiplied by the total number of events across a particular category. So that's just breaking down this NI into these two terms here. And then there's sort of two, there's a very common choice for modeling how the uncertainty on an overall yield looks like at the LHC, and that's to use these log normal type uncertainty. So we think about the total number of events scaling with the with some nuisance parameter delta like this top form here, and the bottom one here is explaining how the fractions of events are modified by variations in these uncorrelated bin by bin uncertainty. So in each case, it's just a product over all the nuisance parameters which have some effect within a given bin. The log normal is a fairly common choice because you can avoid things like going below zero for processes that should only yield positive probabilities. Okay, and so then the other thing we have to deal with is the shape uncertainty, and again, a very common choice for this is to just somehow interpolate between the alternative shapes. So in the slide here, you can see these sort of green and pink lines. These are supposed to represent somehow the interval of 1 sigma uncertainty. And so if we take these points for each bin, that gives you 3 values to interpolate between. That's the 3 red points. And so of course you can come up with a fairly simple polynomial function in order to just interpolate and extrapolate that. So in the end, that gives us just a formula that we can plug into these terms for the background here. So this is really just putting all together the things that I just mentioned for the different interpretations. So it doesn't really matter what the what that looks like. Don't worry about trying to pick it apart. What's really important is to identify the terms that I need to specify now in order to fully specify my likelihood. Right? So as long as I've got this form, what I really need to do is just specify the things in blue. And those are super easy, right? Because they're just the number of events that I observed in the data. And for a particular BSM theory, the number of signal events I expect to see in a given bin. And then there's these terms in red, right? And I can tell you now that most of our time working on an analysis of the LHC is actually spent deriving these terms, effectively deriving these terms. That's really what we care about, right? That's the bulk of our work. The rest of it is actually not most of our time. So that's great, right? So fairly recently, there's been an effort to actually just put this data out there, right? So just publish that data. So by specifying this form and then by specifying each of these input numbers, you can really reproduce the full likelihood. And there's this Python-based tool which was developed in the last few years, which is designed exactly to do that, to allow experiments to actually publish this full likelihood. So you can read the various links there. So you can read the paper from this link at the top, and also you can see a nice talk at one of our reinterpretation workshops if you follow the link on the bottom left. But the upshot is this plot on the right here, which is a comparison of the exclusion contour that you would get using this new tool, this PyHF, which is this sort of dark red line. Oh, sorry, this sort of palish or pinkish red line. and the same thing that you would get using the sort of the framework that was used inside the experiment. And you can't actually see what that other line looks like because it's really directly under this brown line, right? So in terms of reproducibility, this is sort of the gold standard, right? So what the Atlas experiment did and what you as an outside user can do are really exactly the same in this case. So that's really fantastic. Okay, so then this is just another example, really just showing something that I pulled off HEP data. So in this case, this particular analysis had something like 14 bins, something like 100 nuisance parameters, and provides additional things to allow you to swap out different signals for different points in this mass plane. And you can see a bunch more if you just follow the link here. These are a bunch of papers that all provide this information. Okay, so that's great, and we can provide that data, but one thing that's sort of worth keeping track of is the complexity that that we get to when we start to publish this information. So if we go back to our simple toy search, we can sort of try and count how many different terms are needed in order to do that full likelihood specification. So as I said, we had these 90 bins, and so of course you have 90 observations, one for each bin, and 90 expected signal yields. Okay. Then when you look at this box in green, this is telling you how the total number of background events in each category varies, and so you end up with one of these terms per category, which gives you something like 9 additional terms. Then the terms in the middle here are the functions that tell you how the shapes affect different the different bins, so the uncertainties affect the different bins. And if you count up the number of inputs that you need to that, you end up with something like 450. And then you have these additional uncorrelated terms at the end, which are again another 90 or so inputs. So for this toy search, we need something like 729 numbers to fully specify what that likelihood is. Okay, so the one sort of way of simplifying the number of terms that are needed is to somehow collapse the information of all of these terms at the bottom, these green, red, and orange terms, which are really sort of driving the number of things that we need. Collapse that information into a sort of more compact form. And to do this, we can just re-parameterize the background yields in terms of total backgrounds as a function of combined uncertainties. And so I'm going to try and explain exactly how we do that. So you can imagine each of these bins, for each of these bins, generating random values and sampling from the distribution and recalculating, so sampling from the distribution of nuisance parameters and recalculating for each bin what the number of entries or expected entries in each bin is going to be, and then looking at the distributions. So this is just a particular example. So if you look at this green slice, this is bin number 4. So this is the total number of background events for bin 4. This is the distribution of those events when I've sampled over those different nuisance parameters. So you can probably guess by just looking at it, rather than having all of these different inputs to describe what that number is, I can essentially summarize it by just a mean and a variance, right? So this looks fairly Gaussian, and so I really only need 2 numbers to actually specify all of that information, rather than the 40 odd or whatever it was to define all the interpolations. In some cases, you don't end up with something which looks super Gaussian. For example, here, when I'm looking at bin number 62, this is a particularly skewed distribution. And so in this case, it might be relevant to include information about the third moment. So in that case, you really only need, now it's 1 additional piece of information that you can get from the distribution. So it's still only 3 instead of 40 something. Okay, so the idea is that once you can do this approximation, you should somehow be able to just replace the 700 odd parameter or inputs with fewer inputs, basically just describing the distributions that we have for these backgrounds. So using this idea of reporting the distributions in terms of moments rather than the individual nuisance parameters is a way of somehow compressing that data. So it's fairly easy to do. You can find all the details actually in this paper that I linked at the bottom here. But if you just express this number of background events as a simple quadratic function for each of the bins, then using the information, so of course, if you do that, you re-parameterize the likelihood in terms of this new NBI, so you just plug it in here. Then everything else stays the same, except that you have this additional term at the end, which really describes the correlation between the bins. So once you sort of replace the likelihood with this form, now you can just sort of use the moments to actually build up what those individual terms will be for those quadratics. So the formula aren't particularly nice to go through, and I won't bother. You can find all the details again in this paper, but suffice to say that once you have the first, second, and third moments from the distribution that you evaluate with toys, you can just reproduce this sort of simplified version of the likelihood, because you can calculate what these coefficients AI, BI, and CI are, and you can also calculate this row. And this is exactly how you get the moments. So you go to your toy distributions and you just evaluate some fairly simple things. I mean, these are standard things that you can use any number of statistics packages to calculate these for you. And then again, once you have those, you can calculate the inputs that you need to express this simplified likelihood. Maybe I won't bother going into details about this thing. Okay. All right, so the idea might be that, okay, so we've done this compression now for the simplified likelihood, and it's something where we can specify fewer inputs to report the same information, but how well ultimately does it do? And so this again is a study from that paper before, where we try and compare the distributions for these background yields using the full information. So that's the you can see in this 2D distribution, that's the heat map there, and then using this simplified likelihood. So these green contours are supposed to be showing you what the contours of the distribution look like using this. If you approximate using the simplified likelihood. And you can see that it sort of picks up the shape relatively well. And if you project out onto just a single axis, you can see that the green and the black histograms here, which are again the simplified and the full likelihood, are almost on top of each other. So in this case, it's doing a very good job of reproducing that distribution. And here are just a bunch more examples for different bins and looking at different bins together. So that's a little bit about how one can do this simplification, the simplified likelihood approach, and do a relatively good job of reproducing those background distributions. And in the end, what one cares about is how well you can actually reproduce the physics that was intended from this search. So here we've done the extra step of trying to evaluate a profiled likelihood. Which of course is useful for setting limits and reporting p-values and that kind of thing. And the plot on the right just shows the profile likelihood scan for our different approaches. So the black is what you would get from the full likelihood. So this is if you were somebody working inside the experiment with really all the details, all of those input values that you need to specify the full likelihood. And the green is what you get from just using that simplification. So that simple sort of compression using the summaries of the moments of the distributions gives you the green. So it's really telling you that it's actually quite a good approximation that you can achieve with this simplification. And you could do basically the same inference of the physics as you could with the full information. So there's some links here that if you wanted to look at the code that we used to do this, it's all publicly available. All right, so in the end, what did we actually simplify in the end, or did we actually simplify anything? So in the toy search, for this particular thing, when I'm reducing the information in terms of moments, it's actually the opposite of simplification. So to fully specify the simplified version, we need something like 4,000 terms instead of the 729 that I needed before, right? So I've done all this work, and actually I've given myself even more of a headache because now I have to publish even more information. But the point is that this is for a particular setup, right? So this is for where we have these 90 bins, relatively few nuisance parameters, that kind of thing. So if you look at the plots on the right, I show you what happens when you scale this up in terms of the number of bins and the number of nuisance parameters. So here P is the number of bins. So at the top, it's just this 90 that we had. And Q is a number of nuisance parameters, right? So in our example, we had something like, well, we had 2 shape ones and we had a bunch of other ones, right? So in terms of the simplified likelihood, you can see for fairly low numbers of nuisance parameters, you actually need a lot more information to convey the same likelihood as you would just reporting the full likelihood. But as you dial up the number of nuisance parameters, these things flip around, right? So to specify the full likelihood, suddenly the number of inputs that you need to specify really grows compared to the simplified likelihood, which really just stays flat. And so this is where you have the advantage of this simplification. Is in the case of a typical LHC search, you may end up with something of the order 100 or so nuisance parameters, right? So it's not just a couple of shapes and some, a couple of shape parameters and some efficiencies. There's really many steps in the chain of simulation that we have under control, and there's many different nuisance parameters which go into those likelihoods. And so it's really sort of this end near the sort of 100 mark that we're looking at. And so there you can really see a significant decrease in terms of the number of inputs you need to specify the likelihood. And then you can look at it the other way around as well. If I fix the number of nuisance parameters, so something like 100, and I scale up the number of bins, you can see that the full likelihood is you really need more information for quite a long time before the two start to converge together. So this is really where the simplification comes in when you have a large number of nuisance parameters, especially compared to the number of bins that you have, which is often the case for a typical search of the LHC. Okay, so then what about fitting time as well? So on the one hand, there's the number of inputs that I need. So how much data do I need to, or how much information do I need to specify to an outsider to let them rebuild my likelihood? And then of course there's actually then using that data and fitting it in terms of minimization for the profile likelihood and other statistical tests that you might do. So I had a look at some performance studies that were done using an atlas search. So on the left here, the very left in the green, you can see for different implementations of the likelihood and the minimization, what the sort of overall time is to do a particular fit. And calculate an upper limit, and compare that to what happens when you do this simplification process, where you take all of those inputs and you just simplify them into just a few summary statistics of things like the mean and the covariance. And you can see that you get quite a reasonable drop in terms of the amount of time actually needed to run that fit, which is kind of what you expect. And then on the right here, you can see that for this toy search that we did, I had a similar go. Just using the code that we had set up, and in this case, to use the full information was something like 30 odd seconds on just my MacBook, whereas if I'm using the simplified likelihood approach, it takes the order of about a second. So you can easily find in this case, dramatic sort of speed ups in terms of the fitting time and the statistical inference when you're doing this simplification. So not only are there fewer inputs to deal with, but also the fitting and the form of the likelihood becomes easier to use. Okay, so I just have a couple of slides on maybe ways that we can further improve on what we've sort of seen so far. So essentially, what we're doing is approximating a distribution of this mean for the Poisson probabilities, right? So it's this probability density that we're trying to approximate using this simplified likelihood approach. And the idea being that once you have this probability, we can plug it into a likelihood and do all the same inference that we would do at the LHC. And of course, once you have this likelihood, once you specify the data, then this just becomes a simple function, right? So it's just a function of the parameters of interest and the nuisance parameters. And as we all know, as soon as you have a function that you're trying to approximate, which is potentially in a very high dimensional space, then this is a great space for machine learning to really make a difference, right? So there's been quite a few ideas recently to adopt machine learning approaches to both approximate and communicate the likelihood in a public way. And so this is just one paper which has tried to do this recently, actually using the same toy model that I just described. And here they used a sort of DNN approach to try and approximate this log likelihood object and you know, they had a bunch of different studies about different sampling techniques are the best way to actually train their model. And I think I have the results. Yeah, so you can see on the next slide here, you can see in terms of the accuracy, how well they did. This is that same profile log likelihood plot that I showed before, but this time the blue line is what you get from the full, the full thing, doing everything with all the information. And then for slightly different models of training, what the deep neural net can produce. So you can see, of course, for this profile likelihood, in terms of actually extracting the information on this parameter mu, the DNN is doing a very good job of approximating that, right? So one could actually approximate that full likelihood function using this DNN approach and do a very good job of reproducing the results that we at the LHC would do. And the nice thing about this, of course, is that there are many industry standards for publishing neural nets and other machine learning based things. ONXX, for example, is a great format for publishing these models. And so once you have an industry standard for publishing models and a nice way of approximating our likelihoods, and suddenly you have an industry standard way of publishing likelihoods. And so I think that's a really interesting approach moving forward. There are a couple of variations on that available that other people have looked at. So of course, in some circumstances, it may be complicated to actually evaluate the probabilities themselves. So obtaining the actual likelihood is not always possible. And instead, you can turn to looking at likelihood ratios and trying to learn the likelihood ratios directly instead. And you can see some examples from this paper here where they were looking at fairly simple likelihood forms, but they were able to get pretty good reproducibility for the for the thing that you're actually interested in, which is the negative log likelihood. Okay. Right, so I've been waffling for quite a while now already, and all this time I was supposed to be talking about reinterpretation, and all I've really done is show you how I can reproduce an experimental search or a measurement, right? Which is of course super important, but it's not really the end of the story. And so if we go back to this experimental likelihood or the simplified likelihood, if you look at this part of the likelihood, this mu times ns, this basically is exactly the same in both cases, right? So just changing these ns values to something different allows you to reuse the likelihood, but for some other signal hypothesis. So say you weren't looking for a particular dark matter model, but you are interested in some new scalar that mixes with the Higgs or whatever. You can just calculate what these expected signal yields would be, plug it into exactly the same likelihood, and suddenly you've got a reinterpretation of the same data, right? The same is true for the machine learn-based models as well, by the way. It's just it's easier to see on this for this functional form. Okay, so here's some real sort of life examples of experimental likelihoods converted into simplified likelihoods. So again, there's this nice example from Atlas, which is a supersymmetry search, and they looked at actually comparing the full and the simplified likelihoods. So in each case, what they're doing is they're taking the same likelihood object, they're just swapping out the number of signal events, for a different model, so a different mass point. And you can see that the doing the simplification, they actually also get a very good agreement between the contours that they publish. This is just another example, this time from CMS, to show you again a comparison of a simplified likelihood approach and a full likelihood approach. Again, each different parameter point in space, you're just swapping out the number of signal events for a different prediction based on where you are in this plane, and using the same likelihood for each different point. And again, you can build up a similar, if you compare the black and the green, you see very good agreement. Okay, so then there's one more subtlety which you should really be angry at me about, which is I was supposed to be answering whether or not we as a community can reinterpret data from the LHC. So essentially, just because I have the information necessary to do that doesn't mean necessarily you do, or indeed someone 10 years from now might be able to do. So there's another little piece which we have to worry about. And this is sort of, I try to summarize this in this slide, which is about standard workflows for prediction. So ultimately, once you have the likelihood object and you want to swap out the signal for something else, you need to just be able to come up with a way to predict reliably what that signal will look like. So the standard workflow is just what I have here on the left. So you have some new signal model that you might be interested in. You pipe it through a Monte Carlo generation. There's usually some detector simulation on top. There's a bunch of different tools that we have for that in the community. A lot of these are public, and theorists like to use them. And then some summary of the analysis itself, such that you can perform the same event selection, categorization, in principle also, any calibrations or anything that the experiments did can be included in there. And then, of course, you end up with just a simple counts for each bin for the signal process. And once you plug that into the things we were just discussing before, you have your statistical inference. And there's a whole slew of groups that are doing exactly this. And this slide really just shows a few of them, of the different workflows that are out there. So the other side of what we try and do as experimentalists is really provide as much information as we can to calibrate that process, to calibrate that workflow to make sure that each step is sort of as accurate as possible. And so that includes things like just providing the event generation that we were using, so that the particular parameter settings we used, code snippets, rivet routines, efficiencies, resolutions, that kind of thing to calibrate the detector simulation. And here's an example, a couple of examples where we've done exactly that. So in a particular SUSY analysis from CMS, you can see there were efforts made to try and validate one of these workflows. So this was using MAD analysis to try and validate one of these workflows and provide information about how how the cut flow looks for a particular selection and what the distributions of some important variables look like. So this is all super important to make sure that that information is, those estimates are reliable for the signal yields. So here, just to focus in a little bit more, is just a very recent example from CMS. Again, this is a search for dark matter. This was a recent update with Ubuntu data. And here you can just see a direct comparison of the full simulation from the CMS collaboration in the blue points, compared to, it's the red line is the full CMS, compared to this implementation of Delphi's and MAD analysis in the blue point. So the fact that the ratio you can see that the agreement is all around 1 tells you that one can do a fairly good job of approximating also the efficiencies of the signal for the reconstruction and the selection using these public tools. Another very neat feature, which is sort of fairly recent and is becoming more and more popular, is to also publish things like XML files for evaluating BDT weights. So we already covered ONXX for publishing neural nets, but also if you have BDTs or whatever, Atlas have now started publishing the information necessary to actually evaluate those BDTs. So one can even pipe through a detector simulated set of events through a BDT and really reproduce exactly what the experiments we're using to extract the signal. Okay, so this is again just an example from a few different groups that have done this in practice, taking different results. So maybe I'll just pick up on the one at the bottom here. So this is just a reinterpretation that was done by the group's models using the CMS simplified likelihood for a particular SUSY analysis. And again, so this time the sort of gray line, the black line here is what the experiments publish. And as we've seen before, if the experiments have already done the comparison of likelihoods using the full information and simplified information and showing that's quite good. And now what you see is the additional thing of having a theorist also produce the signal expectations for different points in the parameter space. And this is what you can see with this sort of gray line here. So you can see that it's not quite as good as we saw before, but nevertheless, it gives you a rough idea of where the exclusion contour would be. So this sort of shows that with relatively simple tools, one can actually reproduce contours produced by the experiment. Okay, so the last point I want to sort of discuss a little bit is this idea of preservation. So we talked a little bit about reinterpretations now, both internally and externally. But also I think a big important point for the future is really preservation of data. So of course, this is a slide I stole from Harrison at one of our workshops. And the idea is to sort of think about what's going to happen in 2061 and what are the kind of things that we want to do at that point, and what things are we not doing now that's gonna cause us a hindrance. And I think publishing these likelihood informations and this reinterpretation material is really a step towards that in that direction of making sure we don't shoot ourselves in the foot for future experiments. I should also say that fairly recently, CERN announced a new open data policy in support of open science. So in general, this is not just it's not just a few people that are interested in this, but this is really becoming a big important thing for CERN and naturally therefore for the LHC in terms of making more reproducible, accessible and reinterpretable results from the LHC. Okay, maybe this is probably obvious to you guys that are familiar with software, but of course we're also working on as part of this open data, working on software containers so that we can preserve workflows within the experiment as well. All right, so maybe just to conclude then, so I asked at the start, can we really reinterpret data from the LHC? And the short answer was yes, but the long answer is yes, but of course. So one thing we have to be careful of is being aware of approximations in terms of unfolded measurements. So unfolding measurements was always the classical way of doing this reinterpretation, but there are a number of issues one has to be careful of there. And also approximations in terms of what I call simplified likelihoods, but you can think of it as compressed likelihood information. So these simplifications that we introduce in the likelihood, combining nuisance parameters or compressing them into simple distributions, can result in losses of correlation, losses of higher moments in terms of those distributions, which we may have to worry about. And you may still have to wait a little bit for these large full-scale likelihoods. So certainly there's been a few cases where the full likelihoods have been published, but as we saw in terms of that scaling of nuisance parameters, once you start to get really a lot of information, while publishing the likelihood is still possible, using it on the other hand is going to be a tricky thing. And I think training the community to actually use those super complicated objects are going to be key. And machine learning based solutions are likely going to help us in that direction. And as I mentioned at the end there's a lot of work ongoing in terms of providing additional information for calibrating detector simulations and validating workflows. And the very last point is that with the open data that we have at the moment, of course, this was the thing that was really on the far right of my spectrum. And so, of course, we don't want everyone to have to become a HEP experimental physicist in order to understand our open data. And I should say that this is getting much better with things like software containers and tutorials. And I just wanted to point to the latest workshop that we had where there are a bunch of tutorials on using different reinterpretation flows. And also to check out a fairly new series of workshops really dedicated towards showcasing reinterpretable analyses at the LHC. So do keep your eye on those and sign up to the interpretation mailing list if you're interested. So that's all I had, and thanks very much.
Thank you very much for this really very detailed discussion, very interesting. Sorry that I missed about 2 minutes because of a very unfortunate power outage, but everything worked without that. I don't see any questions in the live notes. I have a couple of questions, but before I ask them, does anyone else has questions? Please speak up, raise your hand. I don't see anything, so I would like to come back to one point which you mentioned, unfolding. So we were discussing this in the context of the HERA data where unfolding has been used, but now we are realizing that we would wish that also the raw data before the unfolding would have been preserved to redo unfolding with simply better parameterizations which are available, or also better generators which are available. And you mentioned this very interesting point that instead of unfolding, do the interpretation in folded space. The likelihoods which you have shown, I looked in detail a little bit on your comparisons with, for instance, for the calibrations. And I saw that there are differences in some bins of 10%, even more. Is this enough for the precision which you are aiming at?
Yeah, so I should have really clarified that I think it's still a bit of a there's still a sort of broad range of requirements from people depending on exactly what type of interpretations they do. So if you speak to somebody that's looking to look whether or not their new model to explain, I don't know, the LHCb anomalies or something is good, then 10% is probably absolutely fine. But if you speak to someone who is doing a precision fit of PDF data, probably 10% is too large. So in this context, for this analysis, 10% is the sort of ballpark that one needs when interpreting in certain exotic models and that kind of thing. But I would say it's something that we're working on to try and push down even more, because ultimately what we want to do is also apply this to the kind of scenarios you were discussing, where you really have precision data that you want to use for reinterpretations.
And
so yeah.
No, please go ahead.
I was going to say, I don't know if that answers the question or whether you meant something different.
The other thing is, so these likelihoods are typically or often one-dimensional, but how do you then exactly fold in multi-dimensional quantities? This is then where the machine learning comes in.
Yeah, so I should say that the when you say one-dimensional, you mean you mean in terms of the data space, right?
Yes, the kinematic variables of
yeah. So here to be clear, if for this kind of likelihood, right, which is really very common. Maybe I'll go back to the. Oh, sorry. Yeah, well, okay, it's here. For this kind of likelihood, which is super common for many different types of analyses, we're just really talking about bins, and these don't have to be bins of a particular observable. They can be bins in different areas of phase space, right? So in principle, if you have 2D, 3D, whatever number of observables, it's just a case of having bins within that observable, right? So once you get to this thing of just multiplying over bins, it doesn't matter anymore the order of the bins or anything like that, right? So yes, you could. So in this example, it could be that these are three completely different observables, and I'm just looking at the number of events in a particular bin, where the bin is defined by three different observables, for example, or as many as you want. Obviously, the problem then comes from actually figuring out what the background is, or figuring out the expectation in the bin, right? Because then you have to generate enough Monte Carlo to actually populate that three-dimensional space or four-dimensional space. And there, I think some of the ideas in terms of using likelihood ratios, which I sort of briefly mentioned, is exactly trying to target that. So it was this slide. Yeah, it was this slide where I was saying essentially, once you go to higher dimensional spaces that you're trying to do your inference in, then actually evaluating these probabilities can essentially become intractable. And it may be that you could never do it. But one thing you can try and do to get around that is instead rely on the fact that you only ever care about a likelihood ratio. And there are ways that there are machine learning methods that can be used to approximate that. And that's a way of getting around that dimensionality. But if you're happy enough, and if you're able to calculate what those probabilities are, then it's just like having more bins, right? So you just need more bins to publish the likelihood.
I have one more question, but before I ask it, I would like to give everyone else the chance to ask a question. I don't see or hear anything. So So let's assume for this use case which you presented at the end, I'm not a member of CMS, but I would like to reinterpret your data, and I would be curious how I would do it just hands-on. So would I more or less use Rihanna to do everything, or would I run a couple of programs? How would this workflow look like? And would I find everything publicly available, or would I have to contact the CMS collaboration and ask for permission to get the data?
Right. So in principle, anything on HEP data is you know, for the taking. So there's no requirement. There's no need to contact CMS people or Atlas people to reinterpret that thing. You mentioned Rihanna here, so that's a particular setup which is a bit more internal to Atlas. So there is some. So I'm not an Atlas person, so I don't know exactly the details. But as I understand, there's one has to make some requests in order to use that. But in general, this workflow on the left, the idea is that someone who's not part of the collaborations can do that. So all of these tools which are listed here are publicly available packages, and these examples that I show here are just groups that have used those packages, plugged them into a workflow themselves, taken the inputs from HEP data, and then provided reinterpretations. So yeah, so at the level of whatever's provided on HEP data in terms of simplified likelihoods and you know, some of these informations to allow you to tune your workflow, everything else is down to the end user to do whatever they want. I should probably say that it's not true that every analysis has every bit of information that you need. It's we're definitely trying to plug holes at the moment, but you know, the more and more we go on, I think the more people are realizing how useful this additional information is, and the more complete and systematic we hope to make the approach of providing the information that one needs to do these reinterpretations. So it's an ongoing effort that we're trying to improve, you know, both Atlas and CMS to make sure that this can be done without you having to send an email to me and asking, okay, how do I do this you know, interpretation?
That's impressive. Last chance for questions. I don't see or hear anything, so let me then just send or end. Thank you very much, Nick, for doing that, for giving this seminar. This was very interesting. A lot of information, and while you used physics beyond the standard model and CMS, or mostly CMS for your discussion, I think a lot of this applies also for nuclear physics. So thank you very much for doing that. Thanks everyone for joining. This was the Software and Computing Roundtable in July. We will have a summer break in August, and then we continue the discussion of analysis in HEP and NP in September, where we talk about analysis methods. Thank you very much, and have a great day, everyone. Bye.
Thanks again.
Bye-bye.
Thank you.
Everyone.